Hi, everybody. Welcome to our next thrilling lecture in CHY 113. Today, we're going to start in on thermochemistry and start to look at the energy that's involved in various chemical and physical processes. First, though, let's go ahead and start out with some of our warm-up questions. A couple of these, just to warn you, are more difficult than what you're used to, because what we're starting to see is the way that material builds up in a course like this. And so some of these questions are going to depend on you being able to use material and to apply skills that we've learned previously in the course. And so keep that in mind as we work through these. And so let's go ahead and bring those up and start out. And so the first calculation that I want you to do is to calculate the mass that is necessary to prepare 250 milliliters of a 0.0750 molar sodium carbonate solution. As usual, go ahead and pause the video now, try to do this calculation and see what you can do. Hopefully you were able to come up with 1.99 grams of sodium carbonate. Next, I want you to find the concentration of chloride ions when we dissolve 2.45 grams of magnesium chloride into 150 milliliters of water. See what you can do. I hope you got a chloride concentration of 0.343 molar. The thing you have to remember here, and that some of you probably forgot, and so those of you who got an answer, for instance, of 0.1715, what you forgot is that there are 2 moles of chloride for every 1 mole of magnesium chloride. And so the 0.175 was the molarity of the magnesium chloride, sorry, 0.1715. That was the molarity of the magnesium chloride, but we get double the amount of chloride because there are 2 chlorides for every 1 unit of the compound. Next, I want you to find the pH when we take 7.5 milliliters of 0.150 molar HCl and dilute that to 250 milliliters. Pause the video, see what you can do. I really hope you came up with a pH of 2.35. Let's go through this one. And so we have 7.50 milliliters of 0.150 molar HCl. We dilute that to 250 milliliters. Okay, I just wanted to write that out before I covered it with my screen here. And so the first thing that we even have to do is use our dilution equation to find the new molarity of HCl. Let's remember that our dilution equation, M1V1 equals M2V2. The initial molarity of our solution was 0.150 molar, and we took 7.50 milliliters of that. The new molarity is what we're looking for. We diluted that up to 250 milliliters. So we use a little algebra, solve this, we get, so we get 0.15 times 7.5 divided by 250. Oh, that's 0.15. I put it in my calculator wrong. There we go. 0.15 times 7.5. And we get a new molarity of 0.0045 molar HCl. What we have to recognize as well is that HCl is one of our strong acids, meaning it will 100% dissociate into its ions. What that means for us is if we have 0.45 molar HCl, we will also have 0.45 molar H+. And we use that to then calculate our pH, which is equal to the negative log of the H+ ions, the concentration of H+ ions. So we have negative log of 0.45. We put that into our calculator, and I'll just double check. 0.0045, sorry. You just fix those so I don't throw anyone off. Hopefully some of you caught that. These are both 0.0045. That would have really thrown off an answer. Negative log of 0.0045, rounded to 3 significant figures, is in fact 2.35. And so then for our last warm-up question, it involves a titration problem that we went over at the very end of the last lecture. I want you to find the volume in milliliters of a 0.0025 molar NaOH. What volume of that solution is necessary to neutralize 25 milliliters of a 0.00450 molar solution of H2SO4, of sulfuric acid. And so I'll give you a hint on this one. I know some people are sometimes tempted to use the M1V1 equation, but this is not a dilution. You cannot use that equation. Sometimes it'll work just because of coincidence of the way the numbers work out, but for this one, it would not. And so I'll give you a hint. The first thing I would do is set up your balanced chemical equation for this. And then that's all I'll say about this one. So go ahead and try it out and see what you can do. And hopefully you were able to come up with 90 milliliters. And so let's go ahead and go through this. And so again, this is a titration problem, which is nothing more than still basic stoichiometry. The thing is that we are looking for an end volume, and our given information is volume and molarity. That means if we look at our flow chart here, we're basically going right down the middle of our flow chart. We're going right here. We're going from a volume of a solution, use molarity to get to moles, use our stoichiometric ratio to get to moles of whatever it is that we're looking for, and then use the molarity to get to the volume. And so let's go ahead and walk through this one. And so we are starting with, we have 25 milliliters of 0.0045 molar H2SO4. Sorry, let me back up. First thing, we want our balanced chemical equation. That's key for this. And so this is a general acid-base reaction. So we have our H2SO4 plus our NaOH. And so remember that any acid-base reaction is going to form the ionic salt and water. And so just like we've seen in other reactions, it's essentially just a double displacement. Our H is going to come together with our OH. That forms our water. Our Na comes together with our SO4. That forms our ionic salt. And so then we have to find the equation for those. Na is a 1 plus. SO4 is a 2 minus. So we get Na2 SO4, hydrogen's a 1 plus, OH is a 1 minus. We get HOH, which is just water. Sometimes I like to write it as HOH, just because that really allows you to see. I'm just fixing my 2 here. Writing it as HOH really allows you to see what's going on with the H plus coming together with the OH minus in this acid-base displacement. So that allows us to really see that. And then we just want to balance this equation. I'm just going to erase some of this just to clean things up a little bit for us here. And when we balance this, we need 2 NAs here and we need 2 waters. And so this is going to be key for us because what we see is this relationship of 1 H2SO4 to 2 NaOH. So that's going to be important in our stoichiometric ratio. And so we're starting with 25 milliliters of 0.0045 molar H2SO4. I'm just going to convert that to liters just to start off. And so we have 0.025 liters of our H2SO4. We're then going to use the molarity of H2SO4 to convert that over to moles. It's 0.0045 moles of H2SO4 per liter. We'll then use our stoichiometric ratio to convert to moles of NaOH. So we see that there are 2 from our balanced reaction, 2 moles of NaOH to every 1 mole of H2SO4, and then finally our molarity of the NaOH. Remember, the units of molarity are moles per liter, and so I put that into my dimensional analysis setup however I need to. So in this case, I need my moles down bottom and my liters on top. And my molarity of NaOH is 0.00250. I put that into my calculator. Let's make sure we still get the right answer. 0.025 times 0.0045 times 2 divided by 0.0025. And I get an answer of 0.09. Now remember, that's in liters. And so then I'm just going to convert that to milliliters. And I get 90 milliliters. And so that's what I mean when I say we have to start taking into account all of the skills that we've learned. We have to be able to convert between milliliters and liters. We talked about in the very beginning of the course. We have to be able to recognize an acid-base reaction and that the products of an acid-base reaction are our salt plus our water. We have to know how to set up the chemical formula, Na2SO4, because that affects our balancing when we write out the full balanced chemical equation for our 2NaOH, which we ultimately have to use in our stoichiometric ratio here. So that's a lot. And that's what I mean when I tell you that this is a course that builds on itself and we have to keep using the skills that we learn, because we see here that we have to use skills that we've been learning all along. There's no way to solve some of these problems without really applying the things that we've been learning in the course so far. And so that concludes our warm-up questions. Let's go ahead then and launch into some thermochemistry. And so thermochemistry is a subject that deals with all of the different energies that are involved in chemical processes. And actually not just chemical processes, but we're going to look as well at the energy involved in doing something like melting a block of ice. We'll actually quantify that, how much energy is needed in order to melt something and to change phases. And so the basic outline of the whole topic, we're going to start out by talking about some of the basic principles of energy. We'll talk about something called specific heat capacity and the energy involved in heating, just the basic energy involved in heating and cooling things. We'll talk about the energy involved in changes of state. We'll look at the first law of thermodynamics. It is not that you cannot talk about thermodynamics. We will look at what we call enthalpy changes for chemical reactions and a number of ways that we can go about finding those changes and finding the energy involved in a chemical process. So for today's lecture, though, we're just going to focus on the first two and get a little bit into the third. We'll look at some of the very basics. We'll look at heat capacity, and we'll just start, maybe if I decide there's enough time left, we'll just start to get into some of the changes of state and the energy involved there. And so energy in general, energy is the capacity to do work. And that's just the very basic definition of it, is that energy gives us the ability. Energy is used to do work in some way. It's also involved in the transfer of heat. And so energy can come in the form of heat transfer, heating something up, cooling something down. That's energy flow, moving from one thing to another. Two very basic types of energy. We have kinetic energy and potential energy. Those of you who have taken physics are familiar with those two terms. Kinetic energy is the energy associated with motion. And we would calculate that by using the kinetic energy equation. Kinetic energy equals 1/2 mv squared. We're not going to work with that actual equation in here. Those of you that take physics will work with it quite a bit. But I just show the equation so you see what it is, and you see that the kinetic energy associated with motion, the two factors that go into it are the mass and the velocity of the moving particle, the moving thing. There are lots of different types of kinetic energy. There's thermal kinetic energy, the motion of particles. That's the one that we'll be most often working with, especially later on in the course when we start to talk about things like the properties of gases and the nature of temperature and things like that. There's mechanical energy, kinetic energy, moving a car requires some sort of mechanical kinetic energy, electric, sound, other things like that. That again, we won't get to as much in here, but we will be talking later on about thermal kinetic energy. For this unit, we're mostly going to be looking at potential energy. Those of you who again have taken physics have probably talked about kinetic energy in the terms of potential energy in terms of gravitational potential energy, where an object has a different energy potential depending on where it is in relation to the surface of the earth. You know, if I'm holding something, if I'm just out on my front steps holding something out, and that item's probably 7 feet up in the air, as opposed to if I take that same item to the top of the Empire State Building, you know, if I were to drop the items, then obviously the one that I dropped from the top of the Empire State Building would gather more energy as it drops. And so as I hold them there, they have the one that's higher up has more gravitational potential energy. Again, not something that we'll be talking about in here, and we're not going to talk much about electrostatic potential energy in here either. Really what we're focusing on a lot with this unit is what we call chemical potential. And so how much energy is there possible, or how much energy is involved sort of locked up in chemical bonds, or locked up in some of the interactions between particles, and how much energy does it take to disrupt some of those interactions. The law of conservation of energy, you can probably predict it, very, very similar to the law of conservation of mass. Law of conservation of energy states that energy can't be created or destroyed. And so the total amount of energy in the universe remains a constant. And we express that, and we're not going to use this much in here, but we express that as something called a delta U, where delta stands for change, U just stands for overall energy. And so the change in energy would equal 0 because it never actually changes in the whole universe, thinking about the conservation of energy. Overall energy in general, total energy as a result of Q, which we will talk about. Q is the heat energy plus the work energy. And so think about that maybe in terms of like the energy involved in the combustion reaction for fuel that moves your car. So the total amount of energy involved there is the energy of heat from that combustion reaction. That's why things in the engine heat up, and just in general, things heat up as part of a combustion reaction. But then also the energy involved in the work, the energy involved in the motion of your vehicle. That's the total energy involved in that whole process. At the molecular level, so again, this is really what we're more we'll be concerned about in this class. Kinetic energy is associated with the motion of particles. Potential energy is associated with the arrangement of those particles. And so how much energy is sort of inherent in the way that atoms are bonded together and the way that atoms are arranged. Heat. So we're going to talk a lot about heat, and that's really the big sort of energy flow that we'll be looking at for this course. And so heat is just the transfer of thermal energy. Always moves from hotter to colder, always, always, always. And so that's just the direction of heat and energy flow, is from something that's warmer to something that is colder, or from a higher kinetic energy state to a lower kinetic energy. The symbol that we use for heat is Q. So when we say Q equals whatever, what we mean is that Q equals the heat, the thermal energy flow associated with that process. And we're going to see that a lot. We're going to use Q quite a bit, even just a little bit later in this lecture. When we look at heat in general, when we look at our transfer of energy, we do have to keep in mind extensive versus intensive properties. And so remember that an extensive property is a property that depends on how much of the material is actually present. Something like mass. The mass of something is an extensive property, or it is a physical property. But the mass of something will change depending on how much matter I have. If I have more matter, I have more mass. Similarly, volume. The volume of something is a property of that thing, but it's going to change depending on how much of it I actually have there. Versus an intensive property, which is a property that won't change no matter how much of it you have. The density of 1 thimbleful of water is about 1 gram per milliliter. The density of an entire tub full of water is about 1 gram per milliliter. Things like the changes of state, boiling point, freezing point, Those are all intensive properties. That same thimbleful will boil at 100 degrees, just the same as an entire tubful will boil at 100 degrees. The difference, and this is where we're going to start to get into some of this in this unit, the difference between those two things in that example is the amount of heat that has to be put into the system. You obviously need a lot more heat to boil that tub, but the temperature is the same. And so when we think about heat and temperature, and this is where we have to start to really differentiate between those two things. Heat is simply the transfer of energy from something hotter to something that is colder. And so it's just an energy transfer. And so that means that is an extensive property. The amount of heat that is transferred, the amount of heat that is required for something, will depend on how much of the substance is there. Temperature, however, is a measure of the intensity of that heat. It's not a measure of the amount. So that means that it is an intensive property. It doesn't depend on how much is there. Again, consider those two examples. If I have just a drop, if I have a thimbleful of water that is boiling, or if I have an entire pot full of water that is boiling, so they're both boiling water, they're both at the exact same temperature. They're both at 100 degrees Celsius. That's the boiling point of water. Doesn't matter how much of it you have. But the heat that is involved is much different. There is a lot more heat in that pot of boiling water compared to the drop or the thimbleful of boiling water. And so that means, and the reason there is more heat is because there is more mass in that pot of boiling water. That's the other reason that if it's kind of sort of the same idea, so I've got a boiling thimbleful versus a boiling pot of water. If I take that boiling thimbleful and I dump that on my hand, or I spill that on my hand, that's going to sting a little, but I'm going to pretty much shake that off and I'm probably going to be okay. If I take a pot of boiling water and I dunk my hand in it, or I dump an entire pot of boiling water on my hand, now I've got a problem. There's so much more heat in there that's probably going to leave a mark, and that's not going to be good for me because there's a lot more heat in there because it's dependent on the mass that's involved. And so we have to differentiate that. We're going to do a lot of math in this unit. We're going to be doing a lot of different energy calculations, and so we have to look at the units involved in energy. We use the unit of the joule, and the symbol for that is a capital J. That is the official scientific, the official scientific unit of energy is a joule. These are what it breaks down to. The joule is a derived unit, just like some others we talked about. So a joule is equal to 1 kilogram meter squared per second squared. Don't worry about that. I just like to show it for reference. Quite often with a lot of what we talk about in chemistry, we're actually in the realm of kilojoules. And so you'll see kilojoules for a lot of different units. We will also use calories, capital C for some things, and then calories lowercase c for others. 1 calorie, lowercase c, is equal to 4.184 joules. That is an exact conversion factor. 1 calorie, uppercase c, is equal to 1,000 calories, lowercase c. And so 1 kcal, so to speak. The difference there, calorie with an uppercase c, those are your food calories. When you read a nutrition label and you see, oh my God, my Twinkie, or oh my God, my Ben & Jerry's has 260 calories per serving. 4 servings in this. Crap. That type of calorie is just, or it's a unit of energy. And so literally what you're reading when you read off and get very dismayed because you just ate the entire pint of Cherry Garcia and realize how many calories you had, what you're really seeing is how much chemical potential energy there is within that tub of ice cream. And so that's what food calories are. They're a measure of the energy, the potential energy that's involved in everything that makes that up. And we're actually going to look at a little bit later, maybe in this lecture, but if not, it'll be tomorrow, the next lecture, we're actually going to look at how they determine that, how they are able to find that number of food calories. But that's that relationship. Calories with a capital C are your food calories, which are equal to 1,000 calories with a lowercase c. And we will use this unit a fair bit. We won't use the kcal. We won't use this one that often. But I just like to point it out so you know what that really is. You know that when you read your food calories, you're looking at the inherent energy involved. Another huge thing that we have to identify when we're looking at energy is what we call the system and the surroundings. The system is anytime you're looking at sort of this idea of energy, the system is the part of the universe, the technical definition, that you are studying. For our purposes, the part of the universe that we're studying is going to be usually like the contents of our beaker, or we'll think of the system as our reaction that is taking place. We could have an open system or a closed system, isolated system. We're actually not going to get into that too much. We're not going to worry about that. But the surroundings is technically, what's going on here, is technically everything else. All the rest of the universe that's outside the system. So that's the technical definition. For our purposes, we're going to be looking at, for instance, the immediate surroundings. And so what we're going to have to think about, and what we're going to be looking at quite a bit, most of all the reactions that we do take place in water. And so typically when we talk about system and surroundings, we've got our beaker here. We'll get fancy, use blue. Ooh, so there's our water. So here's our water in our beaker. Here is our reaction within that water. And so that reaction, that's our system. That's the system that we're looking at. The water is the surroundings. And we always have to keep in mind that when we talk about energy, and you'll see where this comes into play in a little bit, but when we talk about energy, we're usually talking about energy from the perspective of the system, from the perspective of the reaction. Now, our actually, I'll hold off on that. You'll see where that becomes important in just a second. And so, for example, here, just another example of it. There's some surroundings, and then there's our system. And so we look at the direction of energy flow. If energy is coming from the surroundings into the system, then we say that heat is gained, because energy is being gained by the system. Energy is being gained by the reaction. And so our Q value for that, and we're going to be really focused in on signs for all of this energy stuff we talk about. The sign of energy is very important because it shows us the direction of energy flow. So when heat is gained by the system, Q is positive because the energy of the system is increasing. If the system loses energy to the surroundings, then Q is negative. The system is decreasing in energy. The system's losing heat. The system's losing energy. That energy is going out to the surroundings, so the system lost energy, and so Q is negative. And so we do have some different terms for that. In cases where our system is absorbing heat, and so Q is positive, we call that an endothermic process. And so we're absorbing heat, our system is absorbing heat, heat is flowing from the surroundings into the reaction. Versus an exothermic process. In an exothermic process, heat is being lost by the system into the surroundings, and so Q is negative. That's an exothermic process. Now, where we have to be careful is sometimes, depending on the reaction that we're doing, we're actually going to notice these energy changes in the surroundings more so than we do in the system. By that, I mean, take a look at, so here we have just our example of our reaction. Let's say we have an exothermic process. So we have an exothermic reaction. Energy is leaving our system here. So energy is leaving our reaction. So that's exothermic. We just said that Q is going to be negative for an exothermic reaction. But if we're actually performing this reaction, if we're holding on to this beaker, think about what's going to happen to the water. Energy is leaving our reaction, going into the water. And so the water heats up. The water gets warmer. And so that's where you just have to stop and think for a second about what's going on. When anytime we're doing this energy stuff, stop and just think for a second about the direction of energy flow. So if we were performing this reaction, you were holding on to this beaker, you would feel it warm up. But you're feeling it warm up because energy is leaving the reaction, energy is leaving the system and going into the surroundings. And the opposite can absolutely be true. There are processes and there are reactions that are endothermic. So here's our water again. Here's our reaction taking place. If we have an endothermic process in which energy now comes into the reaction or into our interaction, so now this is endothermic. Q is positive because energy is entering into the reaction. Energy is going into the system. So Q is positive, but that means the energy is coming out of the surroundings. Energy is leaving the surroundings to go into the system. If energy is leaving the water, then the water is going to cool down. And so that's, again, where I say you just have to stop and think for a second about this direction of energy flow. If we're running a reaction in water and you feel the water cool down, and there are definitely things that you do, there are even some things that you can dissolve. Don't quote me, but I think something like potassium chloride is an endothermic process when it dissolves. And so when it dissolves, it literally sucks up energy from the water. So you feel it get colder. You would feel that beaker get colder in your hands. However, we would say that Q, we would say the heat involved is a positive number because the system, the reaction is gaining that energy. So it's real important throughout this whole entire unit on energy to stop and think about the direction of energy flow. That's going to be vital in order to get the right signs for a lot of your answers and for just a lot of this energy flow in general, to get the right positive or negative according to our direction of flow. Couple different terms that we're going to start to work with. One is heat capacity. For heat capacity, we use an uppercase C, and so C equals. The heat capacity is the amount of heat that's required to raise the temperature of a substance by 1 degree. Now, this is an extensive property because this doesn't take mass into account yet. The units for heat capacity would be joules per degree C. It's going to depend on how much the temperature changes, the identity of the material, and the amount of matter that there is. Now, this is different. You see these two terms in your book, right in the first section. You should, I'm just making sure. Yeah, right in 5.1, energy basics. So you'll see them talk about differences between heat capacity and specific heat capacity, quite often just called specific heat, which we denote with a lowercase c. And so C equals whatever would be the specific heat capacity. This is the amount of heat required to raise the temperature of a certain amount, the amount of heat required to raise 1 gram of the substance by 1 degree. So now this is an intensive property. It's not going to matter how much of it that we have. The units are joules per gram degree C, and it only will depend on what the identity of the material is. Every different substance will have a different specific heat. You might also see molar heat capacity. The molar heat capacity is pretty much the same as the specific heat capacity, only now instead of looking at the temperature required to raise a gram by 1 degree C, it's the temperature required to raise 1 mole, the temperature of 1 mole by 1 degree. Same idea, only now instead of a gram of the mass, we're looking at how much to raise a temperature of 1 mole. And this just shows you it's just sort of a table of common a table of specific heats of some common materials. This means, and we're going to look at an example of this in a little bit, but this means that this is another tool that we would have to identify some sort of unknown. If we had a sample of unknown metal and we were able to put it through a test and find the specific heat of it, if, for instance, the specific heat turned out to be about 0.90, then we're going to say, okay, well, that metal is probably aluminum. If it has a specific heat a lot lower than that, of about 0.13, that material might be gold. We could couple that with some other tests. We could do a simple test to find the density. If the density was, if I remember right, about 19 grams per milliliter, that's about the density of gold. So this specific heat would give us another tool in order to identify some unknown materials. Now you might also notice here, so just take note that this table gives us specific heat using the unit Kelvin instead of degrees C. We're going to work with Kelvin much more when we talk about gases later in the semester. For now, just know though that Kelvin, and I just point this out because you might see Kelvin in some other resources, even some of my lectures, I might intersperse Kelvin with degrees C in this Thermochem. To convert though, Kelvin is degrees C plus 273, so it's just an addition of 273.15 to the degrees C. What this really means, or what this means for us, is that a change in Kelvin is going to be equal to a change in degrees C. And so a change of 3 Kelvin would also be a change of 3 degrees C. And that's another point too. If you haven't seen this delta used yet, this delta just means change in. And so change in Kelvin, change in degrees C. And so this is important for us because most of the temperature work that we use, that we have in thermochemistry, will be in terms of a change of temperature. And so you might see Kelvin or degrees C used interchangeably. So don't worry about that. Don't let it throw you off. A change in 1 Kelvin is a change in 1 degree C. A change in 150 Kelvin, or a change of 150 Kelvin, is a change of 150 degrees C. And so we could use those interchangeably as long as we're talking about the actual change in temperature, and that's the key difference. This equation right here, Q equals MC delta T. This is going to be one of our workhorses in chemistry. We're going to use this equation a lot, where Q is going to be equal to our energy that is gained or lost as heat. M is equal to the mass of our substance in grams for this equation to work. Delta T equals our change in temperature. And C equals the specific heat that we just talked about. Remember, delta T being a change in temperature, that means it's going to be equal to the final temperature minus the initial temperature. Be sure to order it in that direction and pay attention to your sign, because that'll be a big difference if you get a positive Q or a negative Q. And that tells us, again, the direction of energy flow. So make sure that you are being very particular when you calculate your delta T, that it's always, always, always final minus initial, and incorporate the sign in there. If you've got, if your final temperature was, say 20 degrees C, and your initial temperature was 50 degrees C, then that means that your change is negative 30. We have to incorporate that negative sign into our calculations. So go ahead and try this one. And so 50 grams of water is warmed up from 25.3 degrees C to 33.7 degrees C. And we want to know how much energy that took. So go ahead and pause the video now, plug this into our Q equals MC delta T equation, see what you can come up with. So here would be our setup. And again, you can see, like I was saying here, this is the example that I used. I used Kelvin. So same idea. Don't let that throw you off. It's still going to be the same numbers involved. If you haven't seen this, by the way, so just remember that -1 as an exponent just means the inverse. And so G -1 and K -1 just means 1 over gram, 1 over Kelvin. And so this would be the same thing as saying, when we look at the units, And so if I have joules per gram degree C, I could also write that as joules gram minus 1 degree C minus 1. Same exact thing. And so sometimes in presentations, you might see it written with the -1 because it can be a little bit easier just to write that into a PowerPoint. So anyway, here's our mass. There's our 50 grams. Our temperature change was 8.4. So let's just double check that. Our final temperature was 33.7 minus 25.3. Sure enough, is 8.4 times our specific heat, which we're given for water of 4.184. So we plug that in and we get 1757.3 joules. And my sig figs are definitely off there. Don't worry about that. I'll see if I can fix that later. But just if you noted that this should have 3 significant figures, you're absolutely correct. And so our final answer would have had to had 3 sig figs there. But what I do want you to take note of is you want to get into the habit of, even right for all this energy stuff, when you're calculating energy, when you're calculating heat, get in the habit of writing a positive sign. I know that it's implied and you don't technically need it there, but get in the habit of doing that, just so it makes it easier to keep track of saying, okay, this is definitely positive. The positive sign indicates to us that the energy has increased. And so this was an endothermic process. And that should just make sense to you, right? If we're warming up water, then energy is certainly being transferred into the water. And so energy transfer going into the system is an endothermic process. In this case, the water is our system. Here's another one. How much heat do we need to warm 250 grams of water, which is about a cup or so? So if we're going to warm up 250 grams of water from 22 degrees C to close to the boiling point at about 98 degrees C. And here we just round off the specific heat a little bit, 4.18. And so try to calculate this. See what you can do. Pause the video and see what you can get for an answer. Hopefully you got 7.9 times 10 to the 4th joules. Another one. This time you're actually going to calculate the specific heat. If we're told that it takes 192 joules to raise the temperature of 45 grams of silicone by 6 degrees, calculate the specific heat. So now you just need to apply a little algebra to our heat equation. Q equals mc delta T. You need to solve it for C. Then plug the numbers in. See what you can do. Hopefully you found 0.71 joules per gram degree C. I don't know what that little box is there, some weird formatting. Well, we're solving here for C, and so if Q equals mc delta T, again, if we just want to look at our algebra, Q equals mc delta T, we need to solve for C. So we're going to take Q divided by m delta T. So that's exactly what we're doing here. Our Q divided by m delta T, missing a parenthesis here, but that equals 0.71 joules per gram degree C. And so, similar to density, where specific heat capacity is an intensive property, we can measure the specific heat capacity of something experimentally. And so let's take a look at how we would do that. Let's say we have a piece of hot metal. We've taken a piece of metal and we've heated that up to almost the boiling point of water. We've heated this up to 99.8 degrees C. So in this case, it's 55.0 grams of some metal. So we heat it up to 99.8 degrees C. We then drop it into water, and we know how much water there is. We know we have 225 grams of water, which is at 21.0 degrees C. We drop the metal in. Now think about the processes here. Think about the energy flow. We drop this hot metal down into the water. Heat from the metal is going to escape into the water. And so the metal is going to lose energy. The water is going to gain energy. The law of conservation of energy tells us that those amounts are going to be the same. The sign will be different because the direction of energy flow is different for each, but the amount of energy involved will be the same until we come to what we call a thermal equilibrium, where they are now both at the same temperature. They're both at 23.1 degrees C. And so that should, again, just make intuitive sense. If I take a hot piece of metal, drop it into water, the metal's going to cool down, the water's going to heat up until they both reach the same temperature. And so, like I said, the law of conservation of matter tells us that we can't gain or lose energy. And so the heat that is lost by the metal has to equal the heat that is gained by the water. And so we can set up an equation where the heat lost is going to be equal and opposite to the heat gained. And we'll take a look at how we actually do this in just a second. And so we have this energy transfer where the energy is going to just, and this is just the idea of thermal equilibrium, which is very key to this, that the energy will transfer from the object at a higher temperature to the object at a lower temperature until the temperature of each is the same. And so let's look at how we would set something like this up. And so in this example, we have a 145 gram sample of copper. It's at 100 degrees Celsius. We drop that into 250 grams of water, which is at 25 degrees Celsius. The whole thing reaches thermal equilibrium at 28.8 degrees C. We want to find the specific heat of copper. So actually go ahead and pause the video now and see what you can do. Take everything that we've talked about, and I'll give you a big hint that what you want to do is you want to set up two equations. One for the heat lost by the metal, and one for the heat gained by the water. And you want to set those equal to each other, and then solve for the specific heat of copper, for the specific heat of the metal. Pause the video and see what you can do. Did you get it? I just worked it out again for myself. Hopefully you got 0.385 joules per gram degree C. Let's do this one together. And so remember that our basic relationship here is we're looking at the law of conservation of energy and the heat lost by the metal. I'm going to use a negative for that heat because it's heat being lost by the metal. It's giving that heat away. Heat lost by the metal equals the heat gained by the water. And so we can set up an MC delta T expression for each of these, where we have the mass of the metal. Actually, we're told it's copper, aren't we? So let me just abbreviate that to copper. Save space. The mass of our copper times the C of the copper times the delta T of the copper is going to equal the mass of the water times the C of the water times the delta T of the water. And we were told that the mass of the metal was 145 grams. We're trying to find the specific heat capacity of the copper, so we'll leave that as C. Delta T of the copper, and so remember the copper started at 100 degrees C. It ended at 28.8, and so 28.8 was our final temperature. 28.8 minus 100 is negative 71.2 degrees C. That is all equal then to the mass of the water, which we were told was 250.0 grams, times the C of the water, 4.184 joules per gram degree C, times our delta T of the water. The water went from 25 to 28.8, so positive 3.8 degrees C. Now we just solve this for the C of copper. So the C of our Cu, everything on the right-hand side are 250, and I'm just abbreviating it a little bit just to show the math, times 4.184, times 3.8, then algebraically divide it by, sorry, remember this was negative 145 times a negative 71.2. That gets us to 0.385 joules per gram degree C. So all we're doing, remember the very basics of this, is that the heat lost by the metal must equal the heat gained by the water. And so we can use a delta T expression, or sorry, a MC delta T expression for the metal, set that equal to a delta T expression for the water, and solve for what we're looking for. So try this one now. Try to find the amount of heat that is required to raise the temperature by 15 degrees C of a 100-gram piece of copper. So this one's simpler. Now you're just going to use the specific heat, use Q equals MC delta T, and find the amount of heat required for this energy change. Hopefully you calculated 578 joules. Okay, I was just looking at what happened different with my formatting. 15 versus 15.0. So another example here. Try this one. So here we have an unknown piece of, we have a certain unknown metal. We have the mass of that, 57.4 grams. It's heated up to 99.8 degrees C and then dropped into a beaker of water. Beaker of water has 225 grams of water. The temperature is 21 degrees C before the metal comes into contact. The thermal equilibrium is reached at 23.1 degrees C. You want to find the specific heat of the metal. So this is a completely unknown metal. We want to find the specific heat of it by sending it through this thermal equilibrium process. Pause the video, see what you can do. I'll give you a hint. If you're stuck, same exact process we just looked at with the copper. Set your two different MC delta T expressions equal to each other. Hopefully you got 0.449 joules per, again, gram Kelvin or gram degree C. We can then use a table of specific heats to find the 0.449 is the specific heat of iron. And so this gives us a pretty good clue that our unknown metal is probably iron. And so the last thing that we're going to look at today is to take a little bit of a look, to start to take a look at the energy that's involved in changes of state. And so we have a certain amount of energy that's involved in melting something or the energy involved in vaporizing something. And we're going to talk about the heat of fusion, which is involved with the heat involved with melting something or either melting or solidifying it, or the heat of vaporization, the energy that's involved in either going from the liquid to the gas phase or the reverse, the gas, the liquid phase. And so the big thing that's important to note here, what's key with these phase changes, and we're going to use this a lot probably in the next lecture. We're getting a little bit long now. But the key thing to recognize is that during a phase change, when something is melting or when something is vaporizing, turning from a gas to a liquid, or sorry, a liquid to a gas, during a phase change, the temperature does not change. And so if you have a sample of pure ice, if you have a sample of water, solid water, it's at 0 degrees C, and we start to add energy into that, it's going to melt. But that energy, all the energy going into it, just goes into melting it, just goes into changing the phase until all the water is gone. The temperature will not change as long as it is still melting. If I take that same 500 kilojoules of energy, though, and apply that to iron, that's not enough to get us to the melting point of iron. Now my temperature is going to change. That energy is going to go into a temperature change of the iron because the state is not changing. Let's look at what we call a heating curve, and we'll leave things here for today. So if we have our sample of ice, our sample of solid water, and let's say it's at negative 50 degrees C. So solid water at negative 50 degrees C. We start to warm this up. This water is going to warm up, and the temperature is going to change. The energy is going to go into a temperature change until, let me get my fancy pointer, make this even easier to see. So we're going to go from negative 50 up to, until we get to the melting point at 0 degrees C. Now, all of the energy, all of the energy that we're putting into this ice, now all of it goes into melting. So along this portion of our curve here, our temperature does not change. All of the energy goes from melting as we go from 100% solid here to then 100% liquid right here. Now that we're at 100% liquid, now the energy that we put into this once again goes into raising the temperature. And so we climb up our heating curve. We have liquid water now here. This is pure liquid heating up again until we get to the next temperature of a phase change, until we get to 100 degrees C. That's our boiling point. And so now every bit of energy that we put into this goes into changing us from 100% liquid water here at this point to now 100% gaseous water, 100% steam right here. All of this portion, all of this energy now just went into changing the phase, into us going from a liquid to a gas state. None of the energy went into a temperature change. Until now, finally, we are now at 100% gas. Now energy can go into raising the temperature again. But while something is changing phase, the temperature does not change. And so again, this is where it's important we can really see the difference in temperature and heat, because the temperature along this portion of the curve doesn't change at all, but the heat certainly does. And so what I will simply leave you with at the end is this, and I want you to just ponder this. I'm not going to tell you the answer, but think about this. If you absolutely had to, what would you rather put your hand into? Something that was liquid water at 100 degrees C, or something that was steam at 100 degrees C? Same temperature, but think about which one would ultimately be worse for you. And with that, that is it for today. Don't actually test that, by the way. Disclaimer, do not do that at home or anywhere else, but think about it. Think about if you were forced to, which one would be worse for you. And with that, that is all for today. I do hope everybody has a great day and that you enjoyed some more chemistry today. Have a good day, everyone.